What if I told you a spacecraft launched in 1977 is now so far away that a simple, hello, takes 22+ hours to arrive, and it answers back with a signal so faint it's like trying to hear a whisper from the other side of a continent. Right now, as you watch this, Voyager is drifting through the solar system's dark frontier, and the strangest thing it found out there isn't a planet. It's the invisible boundary where the sun's influence ends. Stay with me, because in a minute I'll explain why scientists still argue about what that wall even is. This defies common sense. Voyager isn't just far, Voyager is time. It flew past Jupiter in 1979 and Saturn in 1980, took images that rewrote textbooks, and then just kept going. No refuel. No repairs. No upgrades. Just a handful of instruments, a fading power supply, and giant antennas on Earth trying to catch a transmission that's basically drowning in cosmic noise. Here's a comparison you can actually visualize. If the inner solar system is a brightly lit city, Voyager is a lone boat that sailed beyond the last lighthouse, into an ocean with no maps. And scientists are genuinely baffled by what it tells us about the boundary out there. Is it a smooth shell? A turbulent foam? A leaky membrane? So what did Voyager actually cross, an edge, or a storm? To understand why that question is so hard, you need the normal science first. The sun constantly blasts out a stream of charged particles called the solar wind. That solar wind inflates a protective bubble around our solar system called the heliosphere, a huge magnetic region that helps block some of the high-energy particles coming from deep space. In the simplest cartoon, it's like a soap bubble. Inside the bubble, the sun's wind dominates, outside, interstellar space dominates. So you'd expect a clean boundary. Cross it once, and everything flips once. This is where things get strange. When Voyager 1 reported signs consistent with crossing what scientists call the heliopause, the rough boundary between solar influence and interstellar space, the transition didn't behave like a neat line on a diagram. Measurements changed, then stabilized, then raised new questions about turbulence, magnetic fields, and how sealed our bubble really is. You might be thinking, why should I care where the sun's bubble ends? Because that boundary influences the radiation environment that can reach the inner solar system over long timescales, it affects how we interpret space weather in a broader sense, and it tells us what future deep space missions are truly up against. By the end of this video, you'll understand why Voyager didn't just leave the solar system, it exposed that we don't fully understand the container we live in. And if you want the next reveal to click instantly, subscribe, because what I'm about to lay out is the 3-clue case Voyager built, 1 clue from particle data, 1 from magnetic fields, and 1 from cosmic rays. Together they tell a story bigger than the spacecraft itself. Now let's run this like detectives, chronologically. In 1977, Voyager 1 and Voyager 2 launch, taking advantage of a rare alignment that let them hop from giant planet to giant planet with gravity assists. Then 1979 to 1981 hits like a science explosion. Jupiter and Saturn encounters deliver results that still echo, volcanic Io, complex ring physics, moons that hint at hidden worlds. But then the mission becomes something else, an outward expedition with no guaranteed ending. Here's where it gets crazy. Voyager's electricity comes from radioactive generators, and every year the power drops. Engineers have to make brutal choices, turn off heaters, shut down instruments, trim systems, just to keep the spacecraft alive a little longer. It becomes a survival game played with watts. In 1990, Voyager 1 turns back and takes the pale blue dot image, Earth as a tiny pixel suspended in sunlight. That wasn't just poetic. It was a preview of what the mission would become, measuring our place by leaving it behind. Then comes the big turning point. In 2012, Voyager 1 reports data consistent with entering interstellar space. Immediately, scientists around the world lock onto a single question: did it truly cross the heliopause, or did it enter some strange, in-between, region that only looks like interstellar space? And then in 2018, Voyager 2 also crosses, giving us a second data point, which is everything in science. Because one weird crossing could be an anomaly. Two crossings on two different paths start to look like structure. Now the cliffhanger: as the years go on, Voyager keeps returning sparse but priceless measurements while its remaining power shrinks. Each new dataset feels like a final page torn from a book that's actively burning. So what do those pages actually say? Here's the main explanation in 3 clues. Stay with me here. First clue: particle pressure drops. Inside the heliosphere, you're swimming in the sun's particle flow. Near the boundary, that environment changes. Voyager measured evidence consistent with leaving the sun-dominated particle soup behind. Second clue: magnetic fields don't behave like a simple fence. Voyager measured magnetic field behavior that supported the idea of a boundary, but not a clean, slam-the-door transition. Think less brick wall, more shoreline, with currents and eddies where properties shift in complicated ways. Third clue: cosmic rays surge. Outside the heliosphere, high-energy particles from the galaxy become more intense. Voyager saw that increase, like stepping out from under an umbrella into rain. Put together, the story is satisfying: the heliopause is real, and Voyager crossed it. But it immediately raises a sharper question: if our shield has a messy edge, how much interstellar stuff leaks in, and how variable is that leak over time? NASA's Voyager team and peer-reviewed studies have described this boundary as a region where different measurements tell different parts of the story, and the definition of crossing keeps being refined. Translation: the frontier is physical, and still mysterious. And just when you think you've got it, second twist. Voyager 1 and Voyager 2 didn't experience the boundary the same way. That suggests the heliosphere isn't a perfect sphere. It may be distorted by the local interstellar magnetic field, and it may breathe with the sun's activity cycle, expanding, contracting, wrinkling, reconnecting. Some models treat the heliopause like a relatively stable surface. Others emphasize turbulence, magnetic reconnection, and porous regions where particles can slip through like smoke through a cracked door. Now connect that to the 2026 era of space news and mission planning. While Voyager is the lone scout whispering from the dark, the next generation of ideas, especially concepts like a dedicated interstellar probe, are being shaped by the same question Voyager forced on us. What does it actually take to travel beyond the sun's influence with reliable communications, power, autonomy, and instruments that can survive decades? So the mystery isn't ending. It's escalating. Is the boundary a border, or a battlefield? I genuinely want to know what you think. Which explanation feels most likely? The heliopause is mostly a smooth shell, a turbulent foam of shifting layers, or a leaky membrane that opens and closes with solar activity? Drop your pick and why. I'll be in the comments reading the best arguments. Because this affects all of us. The heliosphere is part of Earth's long-term radiation environment. It also changes how we think about space travel and shielding, how the interstellar medium interacts with stars, how atmospheres erode under particle bombardment, and even exoplanets, because other stars have their own bubbles, and those bubbles shape what kinds of worlds can stay stable long enough for complex chemistry. The future direction is clear: better heliosphere models, more spacecraft sampling at different angles, and new deep space communication and power systems that don't depend on 1970s constraints. You didn't just learn Voyager is far. You learned what it's measuring for humanity. And here's the hopeful part: Voyager proves exploration isn't only about new launches. It's about extracting maximum knowledge from a tiny machine that refuses to quit. Every extra month of data is a win against distance. But this isn't the only dark frontier story. Next, we'll cover how an interstellar probe could reach hundreds of AU, what the Oort Cloud might really be, and why the Planet 9 debate won't die. Subscribe, because the map ends, and then the real universe starts. Thanks for watching. Voyager didn't just travel outward, it turned the darkness into data. Keep looking up, keep pushing the horizon. See you in the next one.